In this mini lecture, we are going to discuss some alternate units for talking about solution concentrations. So first off, you might be wondering, why we need these different units. And fair enough. I mean, once you have one unit for concentration, we spent a lot of time talking about molarity so far, the question should be asked, well, why would it be useful to have other units? Does a molarity just get the job done? Well, the answer to that question really comes down to a matter of convenience. Yes, you absolutely could use molarity and capture concentrations. However, when you are dealing with extreme situations where we either have a very low, very small molarity or very high molarity, it can be convenient to define a new unit that when you express the concentration of a given quantity in that new unit, it's a much more easier to use quantity. So for example, if you look at the safe levels of lead in drinking water, those have been determined by the Environmental Protection Agency to be 15 parts per billion. Okay, so you guys might have heard this term, parts per billion, being thrown around. And if you were to express this same value of 15 parts per billion in our typical units of molarity, we would have this very tiny value, about 6.61 times 10 to the minus 9 molar. Okay, so obviously working with a value of 15 is a lot nicer than 6.61 times 10 to the minus 9. Okay, so that's our first extreme. If we have these very small concentrations, then alternate units like parts per billion, and we'll see shortly parts per million, become useful. At the other end of the spectrum, if you look at, for example, mixed drinks, you could have concentrations that would be very high, where the solute and solvent are getting pretty close to having the same values, the same amount. So if you look at, say, a strong alcohol, then we're talking about substances, mixtures, that have roughly 40% by volume alcohol, or ethanol in this case, right? And so in this case, we'd be talking about very high units if we're trying to do a molarity calculation. And so using a concentration expressed by a percent by volume or a percent by mass can be much more simple and much easier to use. So long story short, concentration units are simply chosen out of convenience. And what we're going to do here is present 5 standard concentration units that you will see showing up over and over again throughout this class in different contexts. Okay, so what I want to do is start off with a set of definitions. We'll go through the definition of each one of these concentration units, and then we will go through a series of example problems that put these different alternative units for concentration into practice. So the first one up is a so-called mass percentage, right? And as the name implies, mass percent is simply a ratio expressed as a percentage of the solute mass over the solution mass, right? So the mass of just the solute over the mass of the entire solution, multiply by 100, and you have your percent mass, right? In a similar way, volume percentage is expressed as the ratio of solute to solution volume, multiplied by 100 to express it as a percentage, right? So two very related quantities, one just focusing on the mass, of course, and the other on the volume. The third one here is a so-called mass volume percentage, right? And the mass volume percentage is the ratio of the solute mass up top to the solution volume. So we're basically mixing together the first two concentration units, and then once again express this value as a percentage. Okay, and so you will commonly see these 3 alternate concentration units used, when you're dealing with solutions that have a very high concentration. All right, then our final 2 alternative concentration units that we'll be talking about today are used for expressing quantities that have a very small or very low concentration. All right, so we mentioned these in the introductory slide here, parts per million and parts per billion. Okay, so parts per million and parts per billion, they're both ratios of masses. We're looking at solute mass over solution mass, just as we saw in the previous slide. The difference here, rather than multiplying by 100 to get a percentage, we're going to be multiplying by either 1 million, 10 to the 6, or 1 billion, 10 to the 9th, in the case of ppm and ppb respectively. All right, so you can remember parts per million, 10 to the 6, multiplied by a million. Parts per billion, 10 to the 9th, multiplied by 1 billion. Right? So you can see how if you have a very small ratio of the masses here, right, then by multiplying by these large values here, we're going to end up at the end of the day with much more convenient numerical values. Okay, so let's go ahead and work through a couple example problems to see how we can put these different alternate concentration units into practice. First up, let's go ahead and work through a percent by mass problem. In this example, we've got a 5.0 gram sample of spinal fluid, and it contains 3.75 milligrams of glucose. We want to use this information to determine the percent by mass of glucose in this spinal fluid sample. So the first thing we have to do when we're looking at a percent by mass, it's a ratio of masses. But before we can take that ratio of masses, we need to make sure that both of our masses are in the exact same units. You don't want to take a ratio where one's in milligrams and the other's in grams, right? Which is the situation we have here to start things off. So you could pick either one. I decided to go ahead and convert the milligrams into grams, but of course you could go the other direction just as well. So I'm going to take that 3.75 milligrams of glucose, carry out our unit conversion, convert it into grams, and arrive at our 0.00375 grams of glucose. Now, once we're in the same mass units, we can plug those mass values directly into the mass percent equation and take the value from the problem directly, 5 grams of spinal fluid on the bottom, our grams of glucose up top. Take that ratio, multiply by 100, and we arrive at our final answer of 0.075%. All right, so let's go ahead and do one more example using mass percentage. A little bit different format here. So in this problem, we're dealing with a concentrated hydrochloric acid solution, and this concentrated hydrochloric acid solution is 37.2% by mass HCl. Okay? And it turns out this is commonly used in the laboratory. And so what we want to do here is, take this known density of the solution, 1.19 grams per milliliter, and figure out what mass of HCl is actually contained in half a liter of this solution. Okay, so we have a percent by mass, we have a density, and we have a volume. And we need to figure out the mass of that solute, the mass of that HCl. Our first step in solving this problem is to use that density and the total volume of 0.5 liters to determine how many grams of solution we have. Because remember, this is the density of the entire solution, the volume of the entire solution. And so when we're looking at the density is given to us in 1.19 grams per milliliter. So I'm going to take that half a liter and convert it into 500 milliliters of solution, multiply by the density. Notice milliliters cancels out when we do that, and we will be left then with the mass of solution, which is 595 grams of solution. Now, we know that this solution is 37.2% by mass HCl, which means if I were to assume a 100 gram sample, then I know that in that 100 gram sample, there will be 37.2 grams of HCl. So given the massive solution that we just calculated in the first step, we can multiply by this ratio under the assumption of 100 grams of solution, this ratio that we formed, 37.2 grams of HCl per 100 gram solution, to arrive at our final answer. Grams of solution cancels out, and we're left with grams of HCl. So we should get a value of about 221 grams of HCl. For our next example, let's look at a calculation involving volume percentage. So in this example, we're going to look at rubbing alcohol or isopropanol. Usually is sold as a 70% volume aqueous solution. So if the density of the isopropyl alcohol is 0.785 grams per milliliter, we want to figure out how many grams of isopropyl alcohol are actually present in a 355 milliliter bottle of rubbing alcohol. So the first step here is to use this volume percent to determine the volume of isopropyl alcohol in this 355 milliliters of solution. So according to the 70% volume concentration that we're given in the problem, we can take the total volume of solution, 355 milliliters of solution, and then say, well, because it's 70% by volume, we know that of every 100 milliliters of solution, we will have 70 milliliters of isopropyl alcohol. So we're converting milliliters of solution into milliliters of isopropyl alcohol, and we'll arrive at a value of about 248.5 milliliters of isopropyl alcohol. Now that we know the volume of isopropyl alcohol, we can then multiply by the density, 0.785, to cancel out milliliters of isopropyl alcohol and be left with the grams of isopropyl. So the grams in this case comes out to approximately 195 grams. All right, moving on to our third alternate concentration unit here, mass volume percentage. In this example, we're going to look at a physiological saline solution that is used to prepare intravenous fluids. And this solution is comprised of 0.9 grams of solute per 100 milliliters of solution. All right, so what we want to do is to use that mass and that volume to determine the concentration of this solution in mass per volume. All right, so to do this, we're going to obtain a ratio of mass of solute in grams to the volume of solution in milliliters. All right, so this is common practice here. We're going to express mass in grams and volume in milliliters, and then we are going to multiply by 100. So we can plug our solution, the given quantities in the problem in directly because they're already in grams and milliliters, and we will come up with a 0.9% solution, and you typically see a little MV, mass volume. And now remember that some problems, depending on the context, they may require changing mass or volume units. For the purposes of this class, we will be sticking largely to grams and milliliters. And of course, if I want you to do something different, I will make that explicit in the problem. All right, so as our final example here, we're going to talk about those units for expressing very small concentrations, ppm and ppb. And we're going to go back and we're going to look at our lead and tap water example. So recall that the EPA sets the safe concentration of lead to be less than 15 parts per billion, right? And if that concentration exceeds 15 parts per billion, then you're going to have to start taking remedial actions in order to solve that problem, get rid of that extra lead. So what we want to do first is just see how we can convert from ppb into parts per million. Okay, so to convert this 15 ppb into parts per million, we need to build a conversion factor that takes us between the two concentration units. And this is a problem that I oftentimes see students essentially get backwards. So I want to take a second here and work out where this conversion factor comes from. So what we're going to do first is then just compare the definitions of ppm and ppb, right? We're going to compare these two definitions to build up that relationship. So if we look at ppm, parts per million, we're looking at the ratio of solute mass over solution mass, and then we're multiplying by a million, 10 to the 6, okay? So if we just don't change the numerical value at all, but we just do a little math and say, okay, well, I can express 10 to the 6, right? Remember 10 to the 6, I could express 10 to the 6 as 10 to the 9th times 10 to the minus 3rd, right? Remember, multiplying 2 powers of 10 will add the exponents, okay? So if I do that, and then throw in some parentheses to sort of guide the eye here, we will basically recover the definition of parts per billion, ppb. Okay? In other words, we've constructed that conversion factor. We know that if you want to convert between parts per million, right, you basically just need to take parts per billion, multiply by 10 to the -3 in order to get that parts per million. So our conversion factor is this 10 to the -3, and so we can plug that in now. We know that in this problem we are given 15 parts per billion, and so we are going to be, using our conversion factor of 10 to the -3 parts per million for every parts per billion, or plug it in as 1 parts per million is 10 to the 3rd parts per billion, and we'll arrive at our final answer of 0.015 ppm. Okay? And the most common error that I see students make is flipping this conversion factor. Okay? You flipping it and putting the 10 to the 3rd up top. So remember, parts per billion, that's a smaller unit of concentration. So if we're going to a larger unit of parts per million, well, you better be ending up with a smaller value, right? A smaller quantity, and it's got to be smaller to the tune of 3 orders of magnitude. Okay, so continuing this final example here, let's go ahead and take that 15 ppb concentration of lead and determine what mass of lead in micrograms would be contained in a glass of water. Let's assume that glass of water is 300 milliliters. And let's assume that the density of that tap water is 1.00 grams per milliliter. Okay, so our first step here is going to be to take that assumption of the density of tap water and take the mass of that tap water to determine that the mass of that solution, the mass of that glass, all the water in that glass, is 3.00 times 10 to the second. Okay, so just a direct multiplication, because it's 1 gram per milliliter, so not much work to do there, right? But it's important that we change that solution into mass first before we do anything else, because when it comes to calculating that parts per billion, that parts per million is defined as this ratio of the masses. So now that we know the mass of the solution here, in this case, this is our 3 times 10 to the second, okay, we now need to figure out what mass of solute, all right, will be present. So we're going to take our definition of ppb, and we are going to do a little algebraic rearrangement rather, and we're basically going to say, okay, I want to isolate my mass of solute. So I'm going to take mass of solution from the denominator on the right hand side, we're going to move it up to the top on the left hand side, multiplying ppb, so moved it right up here, and then divide both sides by 10 to the 9th. Right, feel free to pause the video there and double check, make sure you understand how I'm carrying out this algebraic manipulation step here. Once you've verified that, you're then all set to take, calculate that mass of solute by plugging in the given values. We know the ppb for lead, 15 ppb. We know the mass of the water, right, the glass of water that we have. We're going to divide by 10 to the 9th, and we will arrive at our mass in units of grams, 4.5 times 10 to the -6 grams. And of course, we were asked to determine this mass in micrograms, so our final step is to convert that gram quantity into micrograms, and we'll find that there are 4.5 micrograms of lead in that glass of water if you're right there at that cusp of the safe levels of lead in drinking water. Okay, so to sum things up, we've talked about 5 alternative concentration units. We talked about mass percent. We talked about volume percent. We talked about this mass volume percentage. And then our 2 units that are used to describe very small concentrations, ppm and ppb. We've seen definitions for all of these, practice problems for each one of them. And I pointed out to you that the reason we have all these units are simply out of convenience. Depending upon the concentration of the mixture that you're studying and you're wanting to talk about, yeah, you'll be likely to pick one of these over the other just based on which one's going to give you the most convenient numbers to work with at the end of the day.